So we're going to finish off this chapter looking at the value of moment of inertia that might be more familiar to us from general physics, and that is the mass moment of inertia. So this picture from our book is of what we call a flywheel. And flywheels are used in a lot of different applications, basically to power something, because the idea is that once we get that flywheel rotating, it tends to stay rotating pretty well, and part of that is because of its shape. This is a situation where moment of inertia is important because the moment of inertia of that flywheel is large because most of the mass is located at the outer edges of its shape. And when we look at the definition of moment of inertia, we'll see that that actually gives it a larger value because of where the mass is. So because of the mass being located further from the axis of rotation, we can think about the definition of moment of inertia that we learned in general physics, which is generally that we are summing all the mass elements times their radius squared. And so for a flywheel shaped like this, where most of its mass is on the outer edges, the radius is larger for most of the mass pieces, which means that overall the moment of inertia of this flywheel is larger. So here we see that again, is that just a definition of the mass moment of inertia is that it's the integral of the mass times the radius squared times dm. And the units of mass moment of inertia are going to be the mass times a distance squared. So anyway, let's come back to what the moment of inertia quantifies. The mass moment of inertia is quantifying an object's resistance to a change in its rotational motion. If you remember, inertia that we were introduced to in the first semester of physics was an object's resistance to a change in its translational motion. Remember, an object at rest tends to stay at rest. An object in motion tends to stay in motion unless acted upon. The mass moment of inertia basically is similar, only it's talking about an object resisting a change in its rotational motion. So rolling, it's talking about how hard it is to get something rolling or spinning, or how hard it is to stop that rolling or spinning. And what determines how large it is again, the sum of the masses times the radius squared. So the mass can be just a single point mass located at some distance away from an axis of rotation, or it could be a little piece of mass, and we might find the moment of inertia through integration. We also come up with the parallel axis theorem, and I'm not going to go through the derivation again because we basically did it for areas. The moment of inertia about a particular axis would be given by the moment of inertia where the axis passes through the center of mass of the object plus the mass of the object times the distance squared, where distance is the distance that we've moved the axis from its original location when it passed through the object's center of mass. This should look really familiar because it's basically the same as the parallel axis theorem we saw before, but it's just talking about mass instead of area. We also have the radius of gyration, and this again is going to be really similar to the definition that we saw before. The way that works is the radius of gyration squared times the mass is equal to the moment of inertia. So if we rearrange this, we can find the radius of gyration. And so similarly to how we said that for the area moment of inertia was if we took all the area and located it at a particular distance from the axis. In this case, it's the same thing, only if we took all the mass of the object and we put it at a single distance away from the axis of rotation, that would be our radius of gyration, and this is how we would calculate it. And we can also do mass moment of inertia for composite bodies, and we're going to look at some examples towards the end of these slides. So the first example that I wanted to look at for finding the moment of inertia is actually doing it through integration. And this one is actually a little bit different because we're going to imagine that this object is made up of a lot of individual disks, and each one of those disks has its own particular moment of inertia. And so the moment of inertia overall can be found by integrating the small increment of the moment of inertia that each little disk will contribute. And we're going to use that those, of course, are disks. And so we want to look at when the axis goes down through the center of the disk. In this picture here, it's the z-axis, but in our picture, it's the y-axis. But basically, we would say that the moment of inertia that we're using is 1/2 mr squared. But since we're using small increments, it's really 1/2, and we're just getting a small bit of the mass times the radius squared. And so integrating all the contributions from the whole stack of disks that we would get that would add up to give this total object, that's going to be how we're going to do our calculation. Oh, and here this should be rho, which is the mass density. Okay, so we're saying that the moment of inertia about the y-axis was found by looking at the small increments, which is 1/2 dm times the radius squared. Now, we have a little bit of work to do. The little element of mass, if we imagine this, the mass would be given by the density times the element of volume that disk represents times its radius squared. And the way that we would write its volume, well, it's really like a circle, so it's pi r squared, and then it has a depth of dy, and then we multiply it by r squared again. So we start collecting like terms. We have 1/2 rho pi, and then we have r to the 4th dy. Now, in our particular picture, of course, we can see that we're going to integrate over y, but I have this r to the 4th, which is the radius of the disk. Now, the radius of the disk is going to be measured in terms of x, so I'll write this as x to the 4th times dy, but it's still not good enough because I have an x there, but a dy, and so I have two different variables. So I'm going to use the equation of the boundary of that shape, where it says that x is equal to y squared. So I can replace the x by y squared and raise that to the 4th power dy. So I'm going to get 1/2 rho pi and y to the 8th power dy. And now I'm ready to integrate. Y is going to go from 0 to 1. So this is going to be 1/2 rho pi y to the 9th divided by 9, and goes to 0 and 1. And so this is going to give me 1/18 times rho pi, and then rho is 5, so it's 5/18 pi, and this is the value for my moment of inertia, and it's going to be measured in slug feet squared. We're not used to slugs, but remember that in our unit of measurements, where we use feet and pounds, pounds is actually a unit of force, and the unit of mass is actually a slug. We hardly ever use it, so we're probably not that familiar with it. Okay, so now we're going to look at some composite parts. And here are some tables of solids for our reference, because we might want to use these when we're using mass moment of inertia. And you can see that things are expressed in terms of mass and dimension. So in this particular shape, object, we have a rod and then a sphere, which is the, so it's a composite object, and so the overall moment of inertia is going to be given by the moment of inertia of the rod plus the moment of inertia of the sphere. But to find each of these, we're going to probably want to use the parallel axis theorem, because the axis of rotation is not through their centroid. And so I included in this slide the moments of inertia for the two shapes and what we would use for their moments of inertia. So let's look at the sphere. Its moment of inertia when the axis goes through its center of mass is 2/5 mr squared, and then using the parallel axis theorem, we would take 2/5 mr squared plus the mass of the sphere, and then how far has the axis moved from the center of mass would be this distance, which would be 450 plus the radius of 100. This is going to be 0.55, and that's because to put it in meters squared. So we get 2/5. The mass of the sphere is 15. Its radius is 0.1 if we measured in meters. 15 times 0.55 squared. And we get an overall moment of inertia for the sphere of 0.4558 kilograms meters squared. If we use the rod, now I'm going to cheat a little bit on the rod, because the rod rotating about its end is something that we use a lot, and it's just 1/3 ml squared. So we don't, that is when it's about the end, like where it is right here. So we don't have to use the parallel axis theorem. If we did, which we kind of did the other day, we would have the 1/12 ml squared plus L over 2 is the distance it moved, and it's going to end up to be 1/3 ml squared. So we're just saving the step. The mass of the rod is 10 kilograms. It's 0.45 meters long, and so its moment of inertia is 0.675 kilograms meters squared. The total is, we're just going to find, is the 4.558 plus 0.675, and it's going to be equal to 5.23 kilograms meters squared. And so that's the overall moment of inertia, mass moment of inertia of this object. And now we're going to do one more, and this one's a little bit more difficult, because notice that we're looking for the moment of inertia for an axis that's perpendicular to the screen and passing through point G. Point G is the center of mass of the two objects together. So we need to find out what y bar is. Y bar, and we're going to measure from the very top. So we're going to take the mass of the rod, which is 3 kilograms, times its center of mass. It's 2 meters long, so it would be half of that, so it's 1. Then we have the 5 kilogram plate, and its center of mass is going to be right in the middle, so it's going to be 2.25. And then we'll divide by 8. So that's going to be, the y bar is 1.78, and it's measured downward, so it's 1.78 meters, measured down from the point O. So every time we use our parallel axis theorem, we need to be finding the distance not from the top to the center of mass, but from point G to wherever the center of mass for each object is. So now we're going to do the plate. And the other thing is we're usually used to the axes to lie in the plane of the object, like this x or y axis. But we're actually thinking about an axis that would correspond to the z-axis. So our expression for our moment of inertia of our plate is this one right here. Well, when the axis goes through its center of mass. So I use 1/12 times the mass of the plate, which is 5. And then I use the dimensions, 0.5 squared plus 1 squared. And then we have to use what's the distance that we've moved the axis. So I'm going to take 2.25, which is the distance from the top to the centroid of the plate, minus 1.78, which is my point G. The difference between those two values is how far we've moved it. And so if we put in our values, we're going to find the moment of inertia is 1.62 kilograms meters squared for this object. Now for the rod, we have 1/12 ml squared plus md squared, so it's 1/12. The mass of the rod is 3. Its length is 2. And then the distance that we're going to move it is, the center of it is at 1 meter, and point G is at 1.78. So it's 0.78 is how far it's moved. And so that gives us a moment of inertia of, for the rod, of 2.83 kilograms meters squared. So our total is 2.83 plus 1.62 is 4.96. Sorry, 4.46 kilograms meters squared. And if I wanted to find the radius of gyration, I use this expression, solve for k. It'd be square root of 4.46 over total mass of 8. And, oh, I didn't calculate it, sorry. But again, remember that is where if we put all the mass of this composite object at a single distance away from the axis to have the same moment of inertia, that is what the radius of gyration is. All right, so now we're done with the chapter 10 totally, and hope you enjoyed it.